course, my English is not so perfectly. It's only my school English and what I have from the literature. And so I hope you will understand me. If you don't understand, please give a sign. Yeah. The question on the origin of life, there is, I begin with a question. Is it the origin of life or is it the origins of life? We don't know. It's a very manifold problem, and I will only speak about the question RNA or proteins first, or RNA precursors or protein precursors. We don't know. The problem we have, I showed you with this line. You see, this shall show you this line is 4.5 meters. This means here is the beginning of the Earth. Oh, yes, thank you. Of the Earth, and that is here I will today. Now only the question: how many centimeters are 1 million years? Only 1 millimeter. 1 millimeter is clear, you know, but that means now we will speak about in this area, and now we are here. Mankind is 100 millimeter. So you know the problem here. And we have many question marks, and I will give a little quotation from one, perhaps the most famous, the most famous researcher in this field, origin of that field, that is the origin. I don't know, you have heard his name, but I mean, he is the most knowledge. He's coming from England, he's working in San Diego, and he's coming from the theoretical chemistry, and he wrote in, I will read a quotation, or there's a book written from Robert Haston, with the name of Genesis in Scientific Quest for Life's Origin. And this quotation I will show you from Bessie Origin. There aren't many facts or opinions about the origin of life that are universally accepted. Can you understand this? Researchers agree that Earth is a little more than 4.5 billion years old. Most would also agree that organisms, more or less like bacteria, evolved in the first billion years of Earth's history, and that Darwinian selection acting on polymeric molecules was involved. Now, but everything else about the origin of life remains obscure. So, and now we will see what we can The title is the very famous RNA world or proteins world. And this question means that RNA, that means information, and then came metabolism, and proteins and peptides, and so you can divide all biochemistry researchers in two groups. The I don't know exactly what they are. Geneticists, okay, yeah. That are the RNA world fans, and the metabolists. We have two groups. But, and now, first I will tell you some things because the RNA world is so very attractive. The discovery that RNA has catalytic activities. That means RNA does not only function as information for information transfer or information carrier, but also as a catalyst. Second, the role of RNA in the translation machinery is, for example, the fact that the peptidyl transferase activity of the ribosome has been associated with the nucleic acid moiety and not with the protein. You know, if you don't know exactly which scientific background you all have, you know, ribosomes consists of proteins and of RNA, ribosomal RNA. And many years, all people working in this field, molecular biologists, thought it's clear that the peptide bond of the ribosome is in the protein, genetic protein. But it isn't so. And therefore, this was the second point about because the RNA world becomes more and more interesting. Yeah, and so now I will repeat. You see, I have listed many questions here. First, the question, life origin of the Earth, or life is coming out of the cosmos. If it's originated on the Earth, of anorganic origin or of organic origin. Here we have panspermia. Here in Sweden, Svante Arrhenius, you know, was one of the defensor for the panspermia, and
he made up the word. I invented that word.
Yeah. And other questions are, which are very hard discussed now. And for life, was it necessary that we have a hot environment or a cold environment? Or here, I told you the problem, or the synthesis of biomolecules in the gas phase, like the very famous experiment from Miller, 53, or on solid surfaces, or in the deep sea, on vents, on hydrothermal vents. So, but now I must learn. Here. Oh, yeah. Yeah. Here it's nearly the same. Synthesis of biomolecules and precursors on the Earth, in the atmosphere, in hydrothermal, thermal, in ice, or coming from the outside, came biomolecules from the coming from the atom transported by comets, by meteorites.
But that just pushes the question somewhere else.
Yes.
That doesn't help us. It's all on the left.
So, I'm sure that you know. The next. You know, we speak about the RNA. You know the scaffold of the RNA. Phosphorus, sugar, phosphorus, sugar, bases, the pyrimidines and purines. And why is it is so difficult to imagine that such a complicated polymer could
synthesized or what?
Could be synthesized on the early Earth without the help of biological catalysis. You know, the sugar here, the ribose, is complicated because it has three functional groups, where the phosphorus or the pyrophosphorus, the phosphorus group must be connected. So, because this system is very complicated, people thought or searched after little more simpler structures. Here you see a structure of one sits from the base, the sugar, phosphorus. Here comes the next, and so on. And this molecule for the left side, this is the so-called peptidyl nucleic acid. It was found. If such things are very well known, please give me a shoulder. I go. Do you know this? No. Yeah. This structure was found in Copenhagen. Not from researchers for the origin of life, but researchers looking for substances in order to cover DNA for medicines. And it was Nielsen in Copenhagen. It's called peptidyl nucleic acid because you see here the well-known peptide bondage, like in the proteins. We will see this later. And the next will show you that this, in order for pre-biological questions, it must be easy to construct the substances you need in order to produce such peptidyl nucleic acid. And this is the amino ethylene. This is hydrogen cyanide, and this is formaldehyde. You get this, and you come to this very easy. It's so you can imagine that this reaction was possible on the early Earth. And but there are some persons which mean it's all too complicated for the origin of life on the early Earth. The next shows you that was the peptidyl RNA. You see B is the base. That is that is normal DNA, and that is other construct. Here we have glycerol nucleic acid. That's a research group in France. So you see, these are two possibilities in order to have a more simple scaffold for the RNA. It's necessary that the distance between the bases is really the same like in the DNA, so that a double helix with hydrogen bonds can be
developed.
Can be developed, yeah. So,
is the second one, the one in the middle,
the middle
DNA by any chance?
DNA is DNA glycerol. I have not spoken about that. It's a peptidyl from.
So nothing to do with TNA. Nothing to do with TNA.
No. So the next is other experiment. Here you have the cytosine, guanosine, and you see, here must be more hydrogen bonds, then it does no matter. With alanine, with one amino acid. But it is necessary to have the D-RNA LDL. You must have the both forms of an amino acid, the D form of the L form, and you get the polymer with the possibility to build up such hydrogen polymers. This it's called alanyl PNA.
So it has to be, the bases have to be C and G. It doesn't work with TNA.
That's normal. They have connected normal bases like in the DNA.
Right. But TNA don't work.
But
T and A. They also work. You are using here C and G as bases. But do T and A also work? T and A.
The other two bases.
Of course.
And but it's interesting that you have an alternating sequence L and D all the time.
Of course. That's the best. This example was Leslie Orgel was very interested in this. It's coming from Göttingen, Friedrichsen.
Mhm.
And the newest one, can you give the next? Yeah, that's the newest one. You see, there's many people looking for new structures, so simple, so that it could be synthesized on the early Earth. You read under prebiotic conditions. Such reactions must be but what does it mean? We do not know exactly which physical parameters we have in the Earth, which temperature, which we don't know exactly the composition of the atmosphere. And we don't know exactly how large was the ocean on the atmosphere. I think we are here in this area, about 3.9 or 4 billion years. And perhaps you can help me on I'm not correct. And therefore, it's also we can do very much experiments, but they are coming from laboratory where you have also many complicated, poor substances, and the early Earth was, we don't know exactly. So, here, this is a very new published. It's glyoxylic acid as a backbone. You see, that is the, here it's the normal RNA. It's RNA. You see, we have two OH. That's the normal. But this is a new substance. This is, you must think here is a C and here's a C. It's a modern form to write. And you see also here the hydrogen is not an instrument. So, and you see, you get first such intermediate, and then you can connect it to such. This is very new because this glyoxalate is a very simple organic compound. So, and now I will point up some weak points of the RNA world, because it's necessary to know. The problems with the synthesis of other weak points. First, the problems with the synthesis of nucleotides and some nucleosides. You must first, nucleoside or nucleotide. Nucleotide means base and sugar connected together as a nucleoside. And if you took the nucleoside and connected with phosphorus in the right position, then you get a nucleotide. Yeah? So, and in order to build up on the prebiotic such substance, it is not easy. The yield is sometimes very low yield. And that's one problem. The next problem is the synthesizing nucleic acid bases. C and adenine and so on. There you must use sometimes not ultimate, sometimes very strong or very high concentrations. For example, it's necessary to use 2.2 moles from cyanide concentration in order to get guanine, this one base, and so on. And there, but it is not but not a thing on the so-called ocean of the early Earth. It is also possible that we have lagoons, or we have little ponds that exactly near volcanoes with warm heat from the ground, so you can concentrate substances. But we don't know exactly. It is possible. So the third point is the exact RNA polymer with D-ester linkage. You must connect it with this here and not here with the next. And if you do it without the catalyst, with the enzyme, you get both here and here and so on. And the fourth point is the instability of ribose. Ribose is very unstable. Its half-life for decomposition is 73 minutes at 100 degrees at pH 7 and 45 years on 0 degrees Celsius. It's no time in this area. And now many prebiotic chemists are looking for metal ions to stabilize. There are some laboratories looking only for such new complexes, some stabilized, for example. And now is a new publication or absorption on surfaces from active minerals, some which can stabilize such molecules. But not so easy to do such research because we don't know exactly under which conditions. So that was the ribose instability. And point 5 is the instability of cytosine. Cytosine is one of the bases. Cytosine is also very instable. It's a desamination. Cytosine has an amino group, and this amino group is very labile.
Unstable.
Yeah, okay. Till example, so cytosine has a half-life time about 340 years at 25 degrees Celsius. Yeah, there is another hypothesis. The early Earth had no cytosine. We had only 3, or we had only 2 bases. But the scientific field of origin of life has a record. Has a record. We have the most hypotheses. But if you think, then it's clear. But now we are going over to the amino acids and to the proteins, the peptides. But one fact is accepted: the synthesis of amino acids is under prebiotic conditions is not complicated. Glycine we have found in the interstellar medium. Perhaps will come the next. The next is alanine. Perhaps we will read it in some years that they found alanine also in one cloud in the cosmos. So, and the polymer. So we have amino acids. Yeah. And so I would like to show you from my from our book from 1975. I will show you. We have listed up all the experiments which are made after Miller, 1973, in order to get molecules for the original type. It's from our, yeah? Yeah. Sorry, it's very small, it's not bad, but you will see. UV, discharge, X-rays, UV, exchange, UV exchange, UV protons, beta, and so on. And you see here the orders, and you see here what outcome. Amino acids, primitive amino acids, primitive amino acids, and amino acids here. Next. Amino acids.
Sorry,
yeah, there are 4 sides. Amino acids, you see, and with 1000 with heat, with 4.5 mega LV electrons, beta, heat, semi-corona Entladungen.
Discharge.
Ja, discharges, ja, und so wieder. 1300 degrees Wolf. And you see, amino acids, all 6. So you see here the authors. We have, there were 4 sides. Yeah, here in the fluid phase, UV light, alpha, UV light, sunlight, beta, gamma, heat, gamma, and here glycine, amino acids also. That means I would, yeah, the same. There are 4 sides. Yeah, and this was 75. So many experiments. And you see, amino acids are very easily synthesized. On the conditions UV and heat of the beta, of the alpha, yeah, many. So that means the way of the synthesis was very easy. And now we will look the next. Yeah, the next. Yeah, this, you see. Yeah, and this is chemistry. This is the reaction. Also from the Miller experiment, we know. And you don't know this reaction, yes? Yeah. Then is a name. Ja, Doctor. Yeah, this is Strecker synthesis. Also, Miller looked after the mechanism, and he found also, and after this reaction was found on 1850. 1850. It's 100, nearly 160 years old. So, yeah, now we go in a little in peptide chemistry. I'm chemist here. Yeah. I will not. If you have amino acids and you take off water, you come to a peptide, here to a tripeptide, and in a protein you have some hundreds. And do you know this? Or is it? You don't. Do you know such things?
No.
Yeah.
No.
No. Yeah. I asked you. I will not you take. You mean he was extreme primitive. I will show you. If you have one amino acid, here and rest R is variable. Here's the amino end, and here's the carboxylic end. Every amino acid has the same structure. We have 20 amino acids. Some we will find in the nature, and we know we must eat proteins, and the proteins must be structured. And if you put them together, you must take away water. That's the problem. You see, water is away. And we get the very famous peptide bound NHCO. CNHCO. And if you have a protein with 500 amino acids, then you have 500 the same structure. Only this parent, the rest, has changed. There we have the simplest, the most simple amino acid is glycine. Here we have only a hydrogen. All other have more or less complicated structures. And they still, if you have the well-known structure helix, they react and build up. So now it's a problem on the prebiotic earth. You also can say now we have pentapeptide, and you see that's if anybody will play with it. Yeah. I have constructed this. I thought this could have here a little model from a water molecule. If you put them together, then the water molecules shall come out, drop out. Yeah, we must, if you eat proteins, we must then up. Because the organism can take over gated proteins, we can only take over amino acids and pick up the plant. So, and now the problem. In order to connect amino acids, they must be lifted up to a higher energetic position, and this we call activated amino acids must be activated in order to build so, and the next, and so we have simply, they are activated on this group, on the carboxylic group, on the, the next, and these are still example, three examples for activated groups in an molecule. Other you say don't come together. This chloride, this is ester, thioester, and this is thiol. And over these groups here we have the preview of the chemistry and a world. There are many worlds in the preview of the chemistry. The so-called thioester world. And the founder is the Nobel laureate de Duve. He has written books over his thioester world. These are thioester. Some energetic substances. Because such substances can come from, in example, from volcanic gases, some from H2S. What's the
Hydrogen sulfide.
hydrogen sulfide. Yeah. And
do you still need external energy like heat and radiation, for example?
In laboratory, you it's very easy to make from amino acids a chloride or a such. But it's a question how it was on the prebiotic earth. Was it possible? And now the question, sometimes I ask my auditors, which substance does this activating in our cells now, in our body?
Enzymes.
Hello?
Enzymes.
No, enzymes help only. Enzymes are only catalysts. In your body, billion times this reaction is running. It's ATP, adenosine ATP. We produce nearly our body-wide ATP every day, but we have only about 10 grams in the body. If you extract the whole person, you get only about 10 grams. It's ATP, very interesting. There are enzymes, some do this, and this was my diploma,
Diploma thesis.
Yeah, over such enzymes. Therefore, I know exactly. It was 29.
Mm-hmm.
Yeah, the simplest method in order to get polymers from to get polymers from amino acids. we think we have amino acids on the earth, on the planet. Where they are coming from is the other question. Yeah? And now the question how to get them together, how to lift them so that they can react to get this connection. The simplest way is heat. And so it was an American professor, Sidney Fox, who thought we take amino acids, heat them under nitrogen, and we look what we will see. And it's very interesting. I have long ago worked also in this area. We get a polymer, but this polymer is not the right protein. It's a proteinoid. It's like a protein. It's about 50 or 60% like a protein and 40% why. You must heat it 100 degrees or 100 up till 180 degrees, and with the heat, some amino acids change. For example, some sulfur amino acids like cysteine, they decompose sulfur, and or amino groups go back also. So you get substance, and you get also such things. Here you have thing. It's coming for other things. It's OH. That was OH on here. Then you get such substances, decatopepiracins. In the English expression, I don't know exactly. Decatopepiracins. That means here is stop. You don't get such a thing. You cannot have in your protein chain. But the proteinoid discussion is now not more so actual. Therefore, we go over. The next, can you show the next? Yeah. In order to get aminos together, or in order to get also in nucleic acids, the sugar together with the base, together with phosphate, you must use condensation agents. These, for example, are very well known, in many laboratories use the condensation. How they react is another question. But here we must also say, well, fantastically. But was it possible that such substances you could find on the early Earth? Question. So the next, and therefore there were and therefore the next group of experiments, for example, in order to get dipeptides. You see here is the glycine, and here you have alanine. The next amino acid. And in Innsbruck, Austria, there's a group working in this area, and they found that copper is able to get them together. And why? The chemists, this electron pair is reacting with this, because this C atom is here electrons is a little positivated, and therefore the connection. He got the dipeptide without he on the normal, but he used very high concentrations of salt, oxides, natrium chloride, sodium chloride, without copper. And he's called Rode, Professor Rode, working in Innsbruck, and now he's looking for he will he is looking to have a higher yield from peptides. It's only a dipeptide, and now he's tripeptides. The next is how much was it? Yeah. From his reaction, he got under optimal conditions 10% of glycine and 5% of alanine are incorporated in small peptides. He called it the salt-induced peptide synthesis. And now he's looking for clay material surface in order to get higher yields from, and he's coming up to 6 glycine, 6 peptide, without heat, without catalyst, only with high concentration of
sodium chloride.
Sodium chloride, and sodium chloride is not impossible. There are little pond where we have had on the early Earth such conditions. You see, it is possible to work with very these compositions without heat and without an enzyme. And can you show the next? Yeah, that's a very new paper from the Salk Institute in La Jolla, in San Diego, California. It's a so-called it is this carbonyl sulfide. You only change in CO2 1 O with sulfur. And we know that about now in volcanic gases we found 1 promille this substance in volcanoes. 1 promille in volcano gases. And they found that over such reaction, if you are not chemist, I will not, you see, you get this is reacting with this, you get this, and here you have 2 possibilities. First, you go near here, you get this intermediate, 1 amino acid, 2, and you get a peptide bond. You see, O and O, it's a typical connection between 2 amino acids. This O is coming from 1, and the amino group from this is this. And this is a very interesting new theory in order to get oligopeptides, and with very easy, this is only the substance, and we don't know exactly, perhaps there was, we had it is clear that we had strong volcanic activities on the early Earth, stronger than today. And there we can assume that also much more gases can come up, and therefore it is not impossible.
So this is basically the condensation agent,
if you
carbonyl sulfide or not? Or what is the main role of it?
You may call it so. We don't call it law.
So what happens to that afterwards? Can you
But
trace
condensation,
just SH
but
minus?
it is very in nature. It is not synthesized in a laboratory, but it's a nature product. Therefore, it's also new steps.
Is this with the organisms that are under the sea and the volcanoes under the sea? Is that what they use this photograph?
I don't know exactly, but we have an expert here. Have you, do you know, is there also an analysis from the hydrothermal vents with this?
I don't know, sir. I don't think so.
Yes.
That's not a routine
Uh-huh.
measurement. No.
I know
But
they
it's
use
probably
sulfur,
there.
but I'm not sure how.
It's another hydrogen sulfide, so it should be.
Oh, this already, now we know what it says. So, and only for such people who is interested in a little peptide chemistry, this intermediate you get also if you are working with phosgene. Phosgene is COCl2, and this is very well known you find in many chemical books. This is well known under the name Leuchtanhydrid or Leuchtkörper. Leucht is known nearly 100 years old. The same intermediate. So, yeah, so from Hong Kong is coming a new paper, and they look all that you see amino acid, and they look at the sulfur. Sulfur oxidized to CO3, and CO3 is reacting with the group here. You get this intermediate, and the next amino acid the next amino acid is coming here, and you see R means rest. And you get a dipeptide, C-O-N-H. And from this you go over to, it means sulfur, and sulfur is also a substance we found in the volcanic surrounding. And volcanism is, there are many papers over the possibility of a volcano, also the gases from the heat from volcano, the minerals in the near of volcanoes, and the
Yes.
Entladung.
Discharges again from
If
lightning.
a volcano
Yeah.
erupts, yeah, you have also electrical discharges. And so there are groups also coming from Russia, from Kamchatka, also there are. But yeah, and the group from out of Hong Kong, it's also a new paper, are working in this field. So, yeah, that was the newest. Yeah, this was only. Yeah, I thought it should be enough. And I will end with some sentence from Robert Shapiro. Robert Shapiro is DNA researcher from New York, and is also very well known in the world of origin of life. And he wrote in one of these books. First, he wrote, there are many things we know exactly in chemistry and physics, and there are nothing to wait for. But in the origin of life, however, if no surprises were forthcoming, that would be the most surprising result of all. Better, I cannot end with a better sentence. Thank you.
Thank you.